I hope I'm audible. Please let me know if not. I hope my screen is visible.
Yes.
Okay. So today we'll be solving some problems related to the annihilator of a subspace of a nonlinear space and subspace of a dual space. Further, we'll solve some problems related to Baire's theorem as well. So basically, we'll be solving an assignment. So let's start. Number one, let V be an infinite dimensional Banach space. Dimensional Banach space. And phi belonging to V star be a non-zero functional, be a non-zero bounded linear functional defined on V. Let Z denote the null space of phi. Let Z denote the null space or the kernel of phi. Null space of phi. Compute Z perp or the annihilator of Z. Now, since Z is a subset of V, we know that Z perp is the set of all those bounded linear functionals f in V star which map all the elements of Z to 0. This is the definition of Z perpendicular. Now we need to compute Z perpendicular where Z is the null space of a bounded linear functional phi which is non-zero. Solution. Let f belonging to Z perp be arbitrary. Then f of Z is 0 for every Z belonging to Z. That means now since Z belongs to Z, we have pi of Z is equal to 0. Therefore, we can say that for every f in Z Z perpendicular, f of x is 0 whenever pi x is 0. Now let x naught belonging to V be such that pi of x naught is non-zero. Then for every x in V, phi of x minus phi x by phi x naught times x naught. So since phi is linear, so by linearity, this is equal to phi x minus phi x by phi x naught times phi x naught, which is nothing but 0. Now, since phi at x minus phi x by phi x naught times x naught is 0, then by star f of x minus phi x by phi x naught times x naught is 0 for every f belonging to Z perp, and this is happening for every x in V. That means, again by linearity, fx minus phi x by phi x naught times fx naught is equal to 0 for every x in V and for every f in Z perp. That means f of x is equal to f of x naught by phi of x naught. Now, since x naught was a fixed element in V, so this is just a constant times phi x for every x in V for every f in Z perp. This implies f belongs to the set of all those functionals on V which are just some scalar multiplication of phi x in V for every f in Z perp. That means we get the perpendicular of Z is a subset of the set of all those functionals which are scalar multiplication of phi. Now we'll show that this subset is actually, this should be actually equal. So for equal, we need to show that the bigger set is contained in the smaller one as well. So now if I denote this as some set S, G belonging to S be arbitrary, then G of X is equal to alpha phi of X for every X in V. So in order to for G to belong, this G will belong to Z perp if G of Z is equal to 0 for every Z in Z. Now G of Z is equal to alpha phi Z. This should be equal to 0 for every Z belonging to Z because it is null space of phi. So this tells us that G belongs to Z perp, and hence the perpendicular of null space of Z, null space of phi is equal to set of all those functionals such that they are some scalar multiplication of phi. This is what we need to find. Please go through the proof. If you find any doubt, please let me know. Yeah. So basically, we have shown that if we have some functional, bounded linear functional, the perpendicular of its kernel or its null space is the set of all those functions which are some scalar multiplication of that functional phi. Next, we'll have a look at the annihilator for the case of subset of a dual space. So, let V is equal to L1, which is the space of all those sequences xn such that summation mod xn is finite, and V star is L infinity. Consider C naught subset of L infinity, which is basically V star. We know that L1 star is the dual space of L1 is uh, equivalent to, or we can say isomorphic to, L infinity. So we are considering C naught. C naught is the space of all sequences converging to 0. Space of all sequences converging to 0 as a subset of L infinity. Now we need to compute perpendicular of C. So let's recall, how do we define the perpendicular for a subspace of the dual space. Suppose V be a non-linear space, and then for M subset of V, we know that M perp is the set of all those functionals in V star such that f of x is equal to 0 for every x in M. Clearly, this is a subset of V star. And for n subset of V star, we define n perp as set of all those points x in V such that fx is equal to 0 for every f in V star. Now this is a subset of V. Moreover, we have a result. Moreover, we have m perp is equal to m closure. We will be using this star often. So here we are taking C naught to be a subset or subspace of V star. So we'll be using this definition in order to find its perpendicular. Now this implies C naught per is equal to set of all those elements x in V. Now V is L1, all those x in V such that f of x is equal to 0 for every f in, oh sorry, this is not V star, this is N, for every f in C naught. So by f in C naught, we mean that f is of the type x times y for every y where this x belongs to C naught. Okay, so we need to see what type of set this C perp is. Now let x belonging to L1 be such that f of x is equal to 0 for every f in C naught. That means yx is equal to 0 for every y in C naught. Now, if I define En is to be the sequence which is 0 everywhere, 1 at nth position. Clearly, this sequence will converge to 0 and hence this belongs to C naught. This implies Enx is equal to 0 for every n in N. This belongs to C naught for every n in N. And that means summation I from 1 to infinity En I x is equal to 0. So this is basically just the nth term because rest of the terms are 0. This is for every n in n, for every n in n. That means x is 0 sequence. This implies x belongs to singleton 0. So this gives us C naught perp is a subset of singleton 0. In fact, since 0 is an element of C naught perp, so that means C naught perp is singleton 0. And this is a subset of V. So in our case, V is L1. Now we actually needed to find C naught perp perp. So now this C naught is a subset of L1. Now we'll be using the definition of perpendicular for the subset of the norm linear space. So this implies C naught perp perp is set of all those functionals in L1 star such that f of x is equal to 0 for every x in C naught perp. Now since C naught perp is just singleton 0, this is all those f in L1 star such that f0 is 0. And since we know that for every functional maps 0 to 0, that means this is whole space L1 star, which is L infinity. Therefore, C naught perp is equal to L infinity. I hope this is fine. Next, I would want you to evaluate double perps in a similar way for C naught naught. Instead of this C naught, I want the space W to be C naught naught, the space of sequences that has all but finite terms 0. Can you please try it? So in that case, we have V to be L1. Again, V star is L infinity. And I take C naught naught subset of L infinity, which is V star star, V star. Now you need to evaluate C naught per. Just try it once and tell me what should it be. Exactly same steps will be followed for C naught naught as well. So in that case also we'll get L infinity. Let's the for record, let me write it again. So question number 3. Let V is equal to L1 and V star is equal to L infinity. Consider C naught naught subset of L infinity, which is V star. Compute C naught naught double. Now again, since C naught is a subset of V star, we have C naught naught perp is equal to set of all those elements x in L1 such that fx is equal to 0 for every f in C naught naught. So for x belonging to L1 such that fx is equal to 0 for every f in C naught naught, we have y x is equal to 0 for every y in C naught naught. Now again, since En, which is same as we defined earlier, 1 at nth position, 0 elsewhere, position, this belongs to C naught naught. We get En x is equal to 0 for every n in n. So this gives us xn is equal to 0 for every n in n, and hence x is equal to 0. Therefore, C naught naught perp is equal to singleton 0, and hence this is a subset of L1 perp, a set of all those f in L1 star such that f of 0 is 0, and this is L1 star, which is L infinity. Exactly same way. In both these questions, question number 2 and 3, we have evaluated the double perp for the case where W is a subspace of the dual space. Now we'll see what happens for the case of when W is just a subspace of the nonlinear space. So in that case, we'll be using this remark star. We can write it as remark. We'll be using this remark star. So let's see how. So let V is equal to L infinity and consider C set of all convergent sequences to be subset of V. This is space of all convergent sequences. Compute C for now. By remark, we know that when M is a subspace of M is a subset of V, in that case, M perp is actually equal to its closure. So this implies C perp is basically C closure. And we know that C closure is, can anyone tell me what will be the closure of C? C is the space of all convergent sequences. So its closure is C itself, because space of all convergent sequences is a closed space. So directly the perp is C. Next, let V is equal to L1. Consider C naught naught space of all sequences such that all but finite terms are not all but finite terms are zero. C naught naught is a subset of L1. Now in this case, compute C naught naught per solution. Again, when we have the subset of the nonlinear space, in that case, its perp is given by its closure. So what is closure of C naught naught in L1? Its closure is C naught, but we are considering C naught naught to be a subset of L1. So we know that C naught naught is a subset of L1, which is a subset of C naught. So I cannot take this closure to be complete C naught because we are in the setup of L1. So instead, this will be just L1. Okay. Since we have considered the norm linear space V to be L1. So we can't go further. In fact, in next part, next question, there will be using the fact that its closure is C naught. So if I take V to be L infinity, C naught naught subset of L infinity, compute C naught naught closure. In this case, again C naught naught perp is equal to C naught naught closure. Now here I can take it to be C naught because we have C naught naught subset of L1 subset of C naught, which is a subset of C, and this is the subset of L infinity. Basically, C naught is a subset of L infinity, and our whole space is L infinity. So in this case, we can take it C naught. Therefore, double perp of C naught naught is C naught. So is it fine? Why we took L1 in the previous question, previous problem, and in this one we got C naught? Let's move to next question. Question number 7. Let V be a Banach space. Let ST be greater than equal to 0. Be a collection of operators. Be a collection of operators in LV such that they satisfies the following conditions. Number 1, S0 for t equals to 0, this is the identity map. Second, S of t1 plus t2 is equal to st1 times st2 for every t1, t2 in positive. And the third property says that for every x in V, limit t decreasing to 0, stx is equal to x, or we can write it as limit t tending to 0 plus st at x is equal to x. Part A says that show that there exists some eta positive and m positive such that norm st is less than equal to m for all 0 less than t less than equal to eta. Solution. So suppose this does not hold. That means I can find a sequence Tn which tends to 0, which basically decreases to 0, and for that Tn, this norm Stn is actually unbounded. So what is this saying? According to this statement, whenever t goes near to 0, our our collection norm st is bounded. So if this does not hold, in that case we can find a sequence tn that is decreasing to 0, but corresponding norm stn is unbounded. So suppose the given statement does not hold. Does not hold. This implies there exists a sequence Tn such that Tn decreases to 0 and the corresponding norm Stn tends to infinity. Or we can say that this is unbounded. Or norm Stn is unbounded. So now since Tn is decreasing to 0 by property 3 of this collection St, we know that this St converges pointwise to the identity operator because Stx is equal to x as t tends to 0. This implies by property 3 limit n tending to infinity Stnx is equal to x for every x in V. So that means we have pointwise convergence. So if you remember, we did some result or a very big theorem that gives a very big statement that we can convert this pointwise convergence to norm boundedness. So that is basically the uniform boundedness principle or the Banach-Steenhouse theorem. I'll just recall it. Recall Banach-Steenhouse theorem. of the uniform boundedness principle. Uniform boundedness principle. It states that if X and Y are two Banach spaces and F is a subset of the space of all bounded linear operators from X to Y, is such that supremum T belonging to F, norm Tx in Y is finite for every X in X. That means we have something pointwise boundedness. Then we have uniform boundedness. Norm T, this is the operator norm. This is finite. So here our collection is STN and it is converging pointwise, hence bounded. So therefore, by uniform boundedness principle, we have supremum norm STN n belonging to n is finite, which is a contradiction to our assumption because we had assumed that norm STN is the sequence norm STN is unbounded. Thus, by contradiction, there exists some eta and m positive, eta strictly positive and m greater than equal to 0 such that norm ST is less than equal to m whenever 0 less than t less than eta. This is what we needed to prove. Part B is that given T naught positive, show that there exists some C positive such that norm ST is less than equal to C for every 0 less than equal to T less than equal to T naught. So that means for every T positive, if for every fixed T naught positive, if I take T to be less than equal to T naught, then the norm should be uniformly bounded. So these ST should be uniformly bounded. Let's prove it. Let eta and m be as in part A, and without loss of generality, I can take m to be strictly greater than 1. Since if m is strictly less than 1, then also norm ST that was less than equal to m, now this is strictly less than 1. This can be taken as less than equal to m naught for some m naught strictly greater than 1. And this m naught can be considered in that case. That. So now let T naught to be at T naught equals to um, some n times eta plus delta for some natural number n and delta strictly less than eta. This implies St naught, this is equal to Sn eta plus delta. Now let's look at the second property of S. This is equal to S n eta times S delta. So n eta is basically eta adding n times. So I can write it as eta plus eta and so on, S delta. Now so the sum is n times, again by property 2. This is S eta to the power n times S delta. This is again by property 2. So this implies norm St naught. This is equal to norm S. So this can be written as less than equal to eta times n norm S delta. Now since eta and delta both are since for all t less than equal to eta, as delta is strictly less than n, we have this is less than equal to norm st is less than equal to m. So by part A, this is less than equal to m to the power n plus 1 by part A, since delta is strictly less than eta. Now we needed to show, we actually wanted to show that norm st is strictly is less than equal to c whenever t is between 0 and t naught. So for t naught, we have seen that this norm is less than equal to m to the power n plus 1. Now we'll try to show that for all t less than t naught, same inequality holds. Now for 0 less than equal to t, strictly less than t naught, we have t equals to n eta plus tau. See, since t naught was equal to n eta plus delta, so a number lesser than this can be written in the form of n eta plus tau, where this tau, where this tau is strictly less than delta, because t is strictly less than t naught. And hence as done above, we have norm st is less than equal to m to the power n plus 1. So taking this m to the power n plus 1 to be equal to c, we get norm st less than equal to c for all 0 less than equal to t less than equal to t naught. That's what we wanted to prove. Now part C, is that if there exists some T naught positive such that norm ST naught is strictly less than 1, show that norm ST tends to 0 as T tends to infinity. Now as T tending to infinity, I can write this T equals to some n T naught plus tau, because eventually as n tends to infinity, this T is tending to infinity. We can take T tending to infinity in any way. Where 0 less than equal to tau less than equal to T naught, and as done in part B, and hence as done in part B, we get norm ST less than equal to norm ST naught bar n times norm S tau. Now, since this tau is fixed and norm ST naught is strictly less than 1, this tends to 0 as n tends to infinity. Hence, norm ST naught is strictly less than 1. That is what we wanted to prove. Therefore, norm ST tends to 0 as T tends to infinity. So I hope this is fine. Okay, then let's move to next question. Question number 8. So it has a big setup. For every positive integer n greater than equal to 1, let Pn greater than equal to 2 be a positive integer. Let xmn for every m from 0 to Pn be points in close interval 0 to 1. Define phi n from C01 to R as phi nf is equal to summation m from 0 to Pn Wmn f at xmn, where Wmn, that's just some real numbers, and we define phi again from C01 to R, such that phi of f is equal to integration 0 to 1 ft dt. Now, for integers j greater than equal to 0, let fjt is just a polynomial t to the power j for every t includes 0 to 1. Show that phi n f converges to phi f for every f belonging to C01 if and only if the following two conditions hold. Supremum n in n summation m from 0 to pn wmn is finite and phi nfj converges to phi fj for every j positive. Now this question seems to be very complicated because it has a big setup, although the proof is not that difficult. So let's start with evaluating norm phi n. Proof. We have firstly, let us evaluate norm phi n. Now, norm phi n, this is the operator norm. So this is defined as supremum mod phi n f by the sup norm of f for every f in C01 minus 0. For any f in C01 minus 0, we have mod phi n f. By definition, this is equal to summation m from 0 to pn wmn f at xmn. Yes, on this definition. Now, since this is a finite sum, and since fxmn is always less than equal to its sup norm, I can take this as this outside. So this is summation m from 0 to pn, and we have this wmn. Did I specify that? Mhm. Hmm. Here we had the sequence wmn, the sequence of from this collection m equals to 0 to pn, the collection of positive real numbers. The collection of positive real numbers, and this happens. So since each wmn is positive, so we don't need to specify the mod. So this is wmn. That means mod phi n f by sup norm of f is less than equal to summation m from 0 to pn wm n for every f in C01 minus 0. And hence this phi n norm is less than equal to the summation m from 0 to pn wm n. Also, since the constant function 1, this belongs to C01 minus 0, we have, and for this f, mod phi n f by sup norm of f is equal to summation m from 0 to pn wmn by 1. So therefore, the operator norm of phi n is equal to summation m from 0 to pn wmn. So this is for every n in n. So let me mark this as number 1. Now suppose we need to show star holds if and only if hash holds. Now suppose equation star holds. Suppose star holds. Therefore, we have phi n f converges to phi f for every f in C01. Now, since C01 is a Banach space, we can use the uniform boundedness principle, and this pointwise convergence will give us uniform boundedness. This implies supremum n in n norm phi n f is finite for every f in C01, and hence by uniform boundedness principle, since C01 is a Banach space, we get supremum n in n norm phi n is finite, since C01 is a Banach space. And what was norm phi n? This summation. Therefore, supremum n in n summation m from 0 to pn wmn is finite. This is the first part of hash. And since fj, so second part says that we should have pointwise convergence for all fj's. Now these fj's are polynomials basically, and which are always continuous. So by pointwise convergence we will get second part as well. And since fj belongs to C01 for every j positive, we get phi n j, phi n fj converges to phi n, sorry, phi fj for every j positive. So this is by directly by star. Hence, hash holds. Conversely, let hash holds. That means we have the two two conditions. Now that means phi n f j converges to phi f j for every j positive, and supremum n in n, I can directly replace that sum by norm phi n. This is less than equal to m for some m positive. Now let G be a polynomial. G be a polynomial. Then clearly I can write this G to be equal to summation j from 0 to some n, where n is the degree of G, some alpha j times fj. Now since this is finite sum, so by algebra of limits, we have phi limit n tending to infinity phi n g. This is limit n tending to infinity phi n summation j from 1 to n alpha j f j, which is summation j from 0 to n alpha j limit n tending to infinity phi n f j, which is summation j from 0 to n alpha j phi f j. So this is phi g. Since phi is linear. Now let f belonging to C01 be arbitrary. So by Weierstrass theorem, we know that in every delta neighborhood of f, we can find a polynomial g. This implies by Weierstrass theorem for delta positive, there exists a polynomial g delta such that norm f minus g delta norm, this is less than delta. We wanted to show that phi and f should converge to phi f. Now for epsilon positive, consider phi n f minus phi f. So this is, I can write it as phi n f minus phi n g delta plus phi n g delta minus phi f plus phi g delta minus phi g delta. Now this is less than equal to mod phi n f minus phi n g delta plus mod phi n g delta minus phi g delta plus mod phi f minus phi g delta. Now this is less than equal to norm phi n times norm f minus g delta plus I can directly write it less than equal to epsilon by 3 because g delta is a polynomial, and we know that for polynomials we have convergence phi and g delta should converge to phi g delta, and plus this is norm phi norm f minus g delta for all n greater than equal to some n, since phi and g delta converges to phi g delta. Okay, now this norm phi n is less than equal to m according by hash, and this is norm f minus g delta plus epsilon by 3 plus norm phi f minus g delta. Now we know that norm f minus g delta is strictly less than delta. So I can make it less than epsilon by 3 plus epsilon by 3 plus epsilon by 3 by taking delta to be equal to minimum of epsilon by 3m and epsilon by 3 norm phi is equal to epsilon for all n greater than equal to n naught, for all n greater than equal to n naught, for all n greater than equal to n naught. Therefore, modulus phi n f minus phi f is less than epsilon for all n greater than equal to n naught, and hence this sequence phi n f converges to phi f for every f in C01. Therefore, star holds. I hope this solution was fine with everyone. Please go through the proof again. If you have any doubt, please let me know. Uh, I'll come back in 5 minutes. Please wait. Till then, please go through the proof. So if you don't have any doubt, let's move ahead. Let's look at some true false problems. One. So let V be an infinite dimensional Banach space. And let Wi, I from 1 to infinity, be a collection of linearly independent vectors in V. The subspace W, which is equal to span of W1, W2, and so on, is closed in V. Solution. Now suppose this W is closed subspace. Now we know that closed subspace of a Banach space is a complete space in itself. So suppose that if possible, W is closed. This implies W is a closed subspace of a Banach space. Hence, it is a complete space in itself. Complete space. Also, we can write this W equal to union n from 1 to infinity Wn, where Wn is span of W1, W2 up to Wn. Because clearly for any vector W in W, it is a linear combination of vectors W1, W2 and so on. So when we take elements in the span of an infinite set, each element is a finite linear combination. So each element can be taken from these vectors Wn. Hence, I can write this W to be equal to this union Wn. Now let's see. Now Wn is a finite dimensional subspace of the subspace of V. Wn is a finite dimensional subspace of V. So this implies Wn is something similar to Rn. We can say that this is equivalent to Rn. So Wn is closed and closure of W minus Wn is not equal to W. That is, Wn complement is not dense in W. Since if Wn complement is dense in W, that means Wn does not have any interior point, because any element in Wn will be an element of W, and clearly its epsilon neighborhood will have some elements in Wn complement because it is dense in W. So therefore does not have any interior point. But clearly Wn is a subspace itself, is a complete matrix space. Complete matrix space. Therefore, we get a contradiction. Hence, Wn complement closure is not equal to W. And this is the definition of nowhere dense. This implies Wn is nowhere dense in W, and W is countable union of these nowhere dense sets. But we know that by Baire's theorem that, let's recall a version of Baire's theorem. I'll recall it. A complete matrix space, complete matrix space. So this is Baire's theorem. Complete matrix space is never a countable union of nowhere dense sets. Now, since W is a complete matrix space, because it is a closed subspace of a Banach space, this is a complete matrix space, we get a contradiction. Hence, W is not closed. Therefore, the given statement is false. Is it fine? Are you all able to comprehend how we use the Baire's theorem? Okay. So number 2, it says that C naught naught is not closed in any Banach space which contains it. Again, the C naught naught is the space of sequences xn, where xn has all but finite terms as 0. That means it has just finitely many non-zero terms, rest of the terms are 0. So suppose C naught naught is closed. Now, uh, for every x in C naught naught, I can clearly write x as summation n from 1 to infinity xn yes, because eventually this sum will be finite sum only. So, so this can be written as sum n from 1 to or k from 1 to n x n k e n k, where x n is the sequence such that it is 0 for n not equal to nk and non-zero for n equals to nk. So I have taken just the non-zero terms, and since it has finitely many non-zero terms, the sum turns out to be the finite sum. So every element, this implies x belongs to span of e1, e2, so on, where en is again the sequence which has 1 at nth position and 0 elsewhere, nth position. This implies again, and in fact, we know that the converse is also true. So C naught is actually equal to C naught naught is equal to span of E1, E2, and so on. So therefore, which is equal to union n from 1 to infinity. So or n and n, wn, where again wn is equal to span of E1, E2, and so on up to En. Then again, as did in part A, the C naught naught cannot be closed. Then again, as done in question number 1, if C naught naught is closed, we will attain a contradiction. Hence, C naught naught is never closed subset of a Banach space. This Banach space is important because closed subset of Banach space is complete, and then only we can use the uh, procedure that we did in part A, first question. So therefore, C naught naught is never a closed subset of a Banach space. Hence, the given statement is true. So I hope this is fine. We have used almost the same thing as we did in the previous question. Question part 3. Let pk.
Nidhi, one question.
Hmm.
Uh, will it be true as well for C0? I mean, I guess I'm just looking at the proof and stating at what step it will fail because I know the C0 is closed, right?
C0 is closed, but can we write it as span of these elements? Because it when we write something in span of infinite vectors,
Mm-hmm.
each vector should be a finite linear combination. So can we write sequences in C naught? C naught are the sequences that are converging to zero, na? So Can we write each element in finite linear combination of EIs?
No, we can't. Yeah.
No, no, no. So I don't think this method can be used for that.
Okay. Thank you.
Hmm. Okay. Let PK denote the space of all polynomials or polynomial in one variable with real coefficients and degree less than or equal to k. It says that then P7 is the space of polynomials with degree less than or equal to 7 is nowhere dense in C01. Now for nowhere dense, we need to see C01 minus P7 exclusion. Now if this is equal to C01, in that case P7 is not nowhere dense. So if this is not equal to C01, this is nowhere dense. Now yes. Now see P7 is a proper, in fact, this is a proper subspace of C01. So this is C01. And in fact, this will form a matrix space as well. So P7 must have some interior points. Now if C01 minus P7, so that means P7 complement P7 complement closure, this is equal to C01. In that case, it says that P7 does not have any interior point. But this is a contradiction. Hence, P7 is nowhere dense. This is true. So we have used the fact that P7 is a proper subspace, in fact, a matrix space uh, of C01. It is a matrix space and proper subspace of C01. Part 4. The set of invertible matrices is nowhere dense in MNR, where MNR is the space of all matrices of order n cross n. Now let A belongs to M and R. This implies A has at most n eigenvalues. A has at most n eigenvalues. That means A minus 1 by k times I is invertible for large k. That means A minus 1 by ki belongs to, let denote W, set of invertible matrices in M and R. So A minus 1 by k times I, this belongs to W for large k, and really A minus 1 by k and I tends to A as kn tends to infinity. Now, since A belonging to M and R was arbitrary, I could find a sequence A minus 1 by Ki in W such that A minus 1 by K and I such that this converges to A. So that means our closure, W closure, is equal to M and R. I claim that this W is open in M and R. Now define f from M and R to R, f of A, not from M and R. F of A is equal to determinant of A. Now this implies W is nothing but F inverse R minus 0. Now since R minus 0 is open, F is continuous. Since F is continuous and R minus 0 is open in R, we get W is open in M and R. This implies M and R minus W closure this is M and R minus W closure W is W is open, W complement is closed, so this closure should be equal to W complement closure. So can anyone tell me from this how can we show that W is not nowhere dense?
Isn't W closure equal to M and R
Um,
sufficient?
Now even I got confused why I proved W is open.
Yeah,
Because its closure complement is the empty set, na?
Yeah,
So
this
this
will be
will
empty. Yeah,
be empty set. Hmm. So directly we'll get W is not nowhere dense. Because its closure, it is dense, therefore it is not nowhere dense, है ना?
yeah,
Nowhere dense. So basically this is the given statement is false. The last, the set of singular matrices is nowhere dense in M and R. Clearly, since its complement is dense, therefore it is not nowhere dense. Sorry. So it is no, since its complement is dense, so it is nowhere dense. Since um, W complement, in previous problem we have seen that W complement is open and dense. That gives us W is closed and closure of X minus W. This is M and R. Therefore, W is nowhere dense. Therefore, the given statement is true. Fine. I hope this is fine. These things turns out to be quite complicated and confusing at the end. So, okay then. In any of the problem, if you have any doubt, please let me know. Or else we can stop here.
thank you, Nidhi.